Somewhere out there is a world where you would weigh 13 kilograms, and another where you would weigh 188. Over the next 2 hours, we are going to stand on 14 of them and work out what each one would do to the body you are lying in right now. Real measurements, real arithmetic, shown as it is done. And by the end, one thing will have become obvious across every single world. The gravity is almost never the thing that kills you. A man in a white pressure suit loses his balance on the moon. He goes down slowly. It takes him about 2.5 times as long to reach the ground as it would take here. The camera keeps running. He rocks onto his side, gets one glove under himself and fails. Then he tries again. On the moon, you would weigh 1/6 of what you weigh now. 80 kilograms becomes 13. That sounds like freedom. It is not. 12 people have stood on that surface, and every one of them found the same thing. At 1/6 gravity, the hard part is not lifting yourself. The hard part is stopping, and the reason is the one thing about your body that does not change when you leave the Earth. Everything in this chapter was filmed by the people it was happening to. That has never been true of anywhere else, and it never has been since. Stand on a set of bathroom scales here, and they read 80 kilograms. Carry the same scales to the moon, step on again, and the needle stops at 13. Nothing has been taken out of you, not one atom. That is the rule this whole film runs on. Your weight is not something you own. It is something a world does to you, and every world does it differently. The moon pulls at 1.62 meters per second every second. The Earth pulls at 9.8. Divide one by the other and you get about 1/6. 1/6. That is the only piece of arithmetic this film will ask you to carry. So what are you standing on? Not soil. Regolith, rock smashed to powder over 4 billion years, with no wind and no water to round off a single edge. Every grain is still sharp. It scours visors, works into the weave of a suit and grinds at the seals. The dust wear on the Apollo suits is still an unsolved problem for anyone planning to stay. Warm it up inside the cabin, and the crews said it smelled of spent gunpowder. Above it, nothing worth calling air. Ground in sunlight reaches 127 degrees. Ground in shadow falls to -173. Nothing moves heat between them, so the line is a step wide, one boot in each, and you hold 300 degrees across your own hips. And a day here runs 29.5 hours. You would wait 2 weeks for sunrise. Now put a body on it. Your weight drops to 1/6. Your mass does not move at all. Mass is how much of you there is. Weight is how hard a world is pulling on that. The moon changes the second number and leaves the first one precisely as it was. Call it asterisk asterisk, the mass you keep asterisk asterisk. And the mass you keep is what makes you dangerous to yourself. Every other gravity in this film is a calculation. We take a planet's mass, divide it by the square of its radius, and out comes a number no human being has ever felt. It is honest arithmetic. It is not experience. Every other number in this film was reached that way. Not one of them has ever been checked against a living body. The moon is the exception. The moon is the only world where the measurement was taken by human beings, wearing cameras, with the film running, and what the film shows is not what the arithmetic predicted. 12 people have stood on it. The first, on the 20th of July, 1969. The last stepped off the surface in December of 1972. And nobody has been back since. Between all of them, 80 hours and 22 minutes outside on the surface. That is a single working week, 1 week of human experience, spread across 3.5 years, and it is the entire data set. Everything anyone knows about how a body behaves on another world comes from those 80 hours. And to put that distance into something you can hold. Voyager 1, the fastest object we have ever thrown out of the solar system, moving at about 17 kilometers every second, would cross the gap between the Earth and the Moon in a little over 6 hours. 6 hours at the speed of our fastest spacecraft, and it is still the only world anyone has touched. And almost immediately they stopped walking. Walking is a controlled fall. You tip forward, catch yourself with the next leg, and repeat, and the speed at which that stops working is set by gravity. On Earth, you break into a run at somewhere around 2 meters per second. On the moon, that threshold arrives at under half of it, so they did something else. Watch the film and you can see them work it out in real time. The first minutes are careful, flat-footed, wrong. Then something changes. They loped. They hopped. They converged on a 2-footed bounding gate that nobody had trained them for, and every crew arrived at independently, because at 1/6 gravity, it is simply what works. Here is what the 6th actually does to you. Your muscles still push with the strength they built on Earth. Your bones still carry Earth's mass, so every step launches you higher and further than you meant to go, and while you are up there, you have a 1/6 of the grip waiting to receive you. You are not lighter, you are less anchored. Momentum is mass multiplied by velocity, and your mass came with you, all of it. So when you are moving across that surface, you carry every bit of the force you would carry here, and the ground has 1/6 of the authority to stop you. You cannot brake, you cannot corner, and once you are down, getting up means lifting a suit that masses about 90 kilograms with arms that have almost nothing to brace against. They fell, repeatedly. It is all on film. Now the correction, because the arithmetic oversells it badly. At 1/6 gravity, a leap that clears half a meter here should clear 3. The Apollo crews never came close. The best jump on record is John Young's on Apollo 16, 42 centimeters. The suit is Y, pressurized to about 1/3 of an atmosphere. It fights every bend of a knee or an elbow, and the life support pack hangs the center of mass behind the body rather than through it. The gravity was 1/6. The clothing was not. So the honest version is this. We know precisely what the moon does to a body inside a suit for a few days. What 1/6 gravity does to an unprotected human being over years, to bone, to muscle, to the heart, nobody has measured. Nobody has ever stayed long enough. We have decades of data from the space station, and it is not the same question. That is 0 gravity, and the losses there are severe. But you cannot draw a straight line from 0 to 1 and assume the middle behaves itself. 1/6 might be almost as ruinous as nothing at all, or it might be nearly enough. Nobody knows because the experiment has never been run. Stand still on it, and the strangeness is not the lightness. It is that nothing settles. Dust thrown up by a boot does not billow, and it does not drift with no air to hold it. Every grain follows a clean arc and lands at the same moment, all together, like a handful of sand thrown across a floor. Shadows have no softness at the edge, and your own body starts reporting weights it has never felt. An arm that costs almost nothing to lift, bolted to a torso that still resists being turned. And there is no sound out there. Not quiet, none. Sound needs air to travel through, and there is no air, so the loudest thing in your world is your own breathing and the fans keeping you alive. You watch your boot come down and hear nothing. You watch a rock roll away downhill in complete silence. So why open a film about distant worlds on the nearest one? Because the moon is the calibration. It is the single point on this whole scale where the number in the readout was checked against a living human being, and the answer came back stranger than the arithmetic had predicted. 1/6 did not make them light. It made them unsteady, and it did it in a way no equation had flagged in advance. Everything after this is calculated. Every weight in the rest of this film comes from a mass, a radius and a division, worlds where the pull has never once been felt, and where the same trap is waiting. Your weight belongs to whatever world you are standing on. Your mass is yours. You take it everywhere, and that is what will hurt. Stand on Mars without a suit, and the first thing that happens is not the thing you would expect. You do not freeze, not immediately. The air is far too thin to carry heat away from you quickly. You do not suffocate either, not in the first seconds. What happens first is that the water on your tongue begins to boil. Mars pulls on you at 38% of Earth's strength. 80 kilograms becomes 30. That is the friendliest number in this entire film. And it belongs to the planet we keep saying we are going to. Mars almost gets your body right, and then it takes it back, in the most literal way available. 4 working rovers have driven across it. Not one of them has ever had to survive it. Here is the number everyone argues about, and it is the one Mars gets right. 3.71 meters per second every second. Divide that by Earth's 9.8 and you get 0.378. Call it 38%. An 80-kilogram body weighs a little over 30 kilograms standing there. Your legs, built for the full weight, would have less than half of it to carry. You could jump 3 times as high as you can hear. You could lift a load that would pin you to the floor at home. Of everywhere in this film, this is the one place your body would feel something close to capable. And it looks almost familiar, which is the trap. There is a sky. It is the wrong color, butterscotch. Dust-loaded, and it turns blue at sunset rather than the other way round, but it is a sky with weather in it. There are dunes. There are dry river channels cut when there was water to cut them. There is frost in the mornings. A day lasts 24 hours and 36 minutes, almost exactly hours. Of all the numbers Mars could have landed on, it landed on that one, close enough that a human circadian rhythm could very nearly keep it without arguing. Temperatures reach 20 degrees at the equator at noon in summer. That is a mild spring afternoon. By night, the same ground falls to 153 below. So what is actually wrong with it? Look at the edge of the planet from orbit, and you can see the whole problem in one glance. There is a haze there, a thin band above the surface. That band is the entire atmosphere, and it is almost nothing. Earth holds about 101,000 pascals of pressure against your skin at sea level. Mars holds about 610, 0.6%, and there is a specific number in aerospace medicine where that stops being uncomfortable and starts being fatal. Call it ***, the boiling line ***. We did not infer this. We landed instruments on the ground and read it off them. Viking measured Martian surface pressure in 1976. Every lander since has carried a barometer, and Curiosity has been logging pressure at Gale Crater, sol after sol, for over a decade. It rises and falls with the seasons as carbon dioxide freezes out onto the winter pole and returns in the spring. This is not a modeled number. It is a reading taken continuously by machines sitting in the place it describes. 4 rovers have driven across that ground, and a 5th Spirit stopped moving in 2010 after 6 years, a wheel that would not turn and a patch of soft sand it could not climb out of. Between them, they have covered tens of kilometers, drilled into rock, sampled the air, and photographed the horizon in every direction. We have more surface data from Mars than from any world except our own. And in all of that, not one of the machines has ever had to keep a body alive. Every single measurement of what Mars does to a human being is a calculation from the physics. The same position we were in with everything in this film except the moon. The boiling line sits at 6,300 pascals. That is the pressure at which water, ordinary water, at the temperature your body already keeps it, turns to vapor without being heated at all. Not because it is hot, because there is nothing pressing on it. On Earth, you would have to climb to about 19 kilometers to reach it, and no mountain on this planet comes close. Mars sits at 610 pascals, not near the line. ***, 10 times below it. ***, there is nowhere on that entire planet, no valley, no crater floor, no lowest point on the map, where the air is thick enough to keep the water in your mouth liquid. So here is what Mars actually is. It is the one world in this film that gets the gravity nearly right. 38%. You're 30 kilograms. A day the same length as the one you are having. A sky and weather and seasons. And none of that matters, because the air is 10 times too thin to keep you liquid. The part everybody worries about, the gravity, the cold, the distance, Mars very nearly passes. The part almost nobody mentions is the part that kills you, and it kills you in under 2 minutes. Now the correction, because the popular version of this is wrong, and it is worth being precise. Your blood does not boil. That is the myth, and it is not what happens. Blood runs in a closed system, held above the outside pressure by your own vessels and your own heart, and it stays liquid. What boils is everything exposed. The film of water on your eyes, the saliva in your mouth, the moisture lining the deepest parts of your lungs, which is not sealed off from the outside at all. You would stay conscious for somewhere between 5 and 15 seconds, and then you would not. And after somewhere around a minute and a half, the damage would stop being reversible. And the part nobody can tell you, what 38% gravity does to a body over years. Not seconds, years. Whether bone thins, whether hearts weaken, whether a child could grow to full height there. Nobody has measured it because nobody has ever been. That is the second time this film has had to say that, and we are 2 worlds in. It will not be the last, and by the end you will notice how often the honest answer is that nobody has checked. Put the suit back on and stand still. The dust is the thing you would notice. It is everywhere in the air permanently, staining the sky and settling on everything, and it is fine enough and electrically charged enough that it clings, the way the lunar dust did, but it never stops arriving. The wind reaches storm speeds, and you would barely feel it. There is so little air that a 100-kilometer-an-hour gale on Mars pushes with about the force of a light breeze here. The storms are real, and they can blot out the sun for months. But they cannot knock you over. Your own movement would feel wrong before anything else did. The moon's problem was that 1/6 of a gravity leaves you unable to stop. 38% is different enough to hold you down, enough to walk normally, enough that a drop tool falls rather than drifts. It just falls slowly, a little over 1.5 times slower than here, and after a week your eyes would stop flagging it. And when the sun goes down, the sky around it turns blue. So why does Mars feel like the destination when the numbers are this bad? Because it is the only world where the failure is a single missing thing. Everything else in this film is wrong in several directions at once. Too hot, too heavy, too dark, too far. Mars is wrong in one. Add air, and almost everything else about the place already fits a human being. That is why we cannot leave it alone. And there is one more thing about that 38%, which is where this film goes next. Mars is a little over half the width of Earth. The next world in this film is barely a third, visibly, obviously smaller, and it pulls on you with almost exactly the same strength. 3.70 against Mars's 3.71. Size is not what sets your weight. We will get to what does. 38%, 30 kilograms, 24 hours and 36 minutes. Mars is not waiting for us. It is the first world in this film that gets close enough to hurt. This is a world you could walk across in a few months. Gray, cratered, airless, and smaller than 2 of the moons orbiting other planets in this solar system. Stand on it, and you would weigh 30.2 kilograms, which is a strange number because it is the number you would weigh on Mars, and Mars is half again as wide. 2 worlds of completely different size, holding a body down with exactly the same strength. One of them is doing something the other is not. The answer is not on the surface. It is about 2,000 kilometers underneath it. Weight comes from 2 things and only 2. How much material is under you and how far you are from the middle of it. More mass pulls harder. More distance pulls weaker, and it weakens fast. Double the distance and the pull drops to 1/4. That second term is the one people forget. A world can be small and still hold you hard, because being small means you get to stand closer to its center. Mercury is a little more than 1/3 of Earth's width. Mars is about half. On the face of it, Mars should win comfortably, and the surface gives you nothing to explain it. It looks like the moon. Gray regolith, craters inside craters, no air to soften an edge or move a grain. There are long cliffs, hundreds of kilometers end to end, where the whole crust buckled as the planet cooled and shrank. One crater is not like the others. Caloris is a basin about 1,500 kilometers across, an impact so violent that the shock traveled through the entire planet and came out the other side, where it left a region of broken, chaotic ground that geologists simply call the weird terrain. Something hit Mercury hard enough that you can see the exit wound on the opposite face. Those cliffs are worth a sentence of their own, because they are the core again, showing through. As Mercury's enormous interior cooled, it contracted, and the solid crust on top had to fold to fit a planet that was getting smaller. The whole world shrank by several kilometers in radius, and the wrinkles are still standing. There is no weather. There is nothing that could be called an atmosphere, only an exosphere, a thin haze of atoms knocked loose from the ground by the solar wind and by meteorites, drifting off into space almost as fast as it arrives. Which means the same problem Mars had, only worse. Nothing to breathe, nothing to press on your skin, and the water in your mouth boiling for the same reason it would there. So the question is simple. How does something this small pull this hard? Mercury holds about half the mass of Mars. Half. And it pulls you down with the same strength. The answer is that Mercury is not really a rocky planet with a core inside it. Mercury is a core with a thin layer of rock on the outside. Call it ***, the metal heart ***. We know that because of how a spacecraft moves. Messenger went into orbit around Mercury in 2011 and stayed for 4 years. A planet's gravity is not perfectly even, it is lumpier where the material underneath is denser, and every one of those lumps tugs on a spacecraft and shifts its path by a measurable amount. Track the orbit precisely enough for long enough, and you can work backwards to the distribution of mass inside a world you have never drilled into. That and the way the whole planet wobbles very slightly as it spins is how we know what Mercury is made of. What came back was a planet that is mostly metal. Mercury's core has a radius of about 2,074 kilometers. The planet's total radius is 2,440. That is 85%. 85% of the way from the center to the surface, you are still inside the core, and part of it is molten. We know because Mercury has a magnetic field, a real global one, about 100th the strength of Earth's, but unmistakably there. A planet only generates a field like that if it has liquid metal moving inside it. Mars does not have one. Mars had one 4 billion years ago, and its core cooled and the field died, which is part of why Mars lost its air. Mercury, far smaller and far older in the sunlight, still has a heart warm enough to turn. For comparison, Earth's core reaches barely half of our radius, and we are the densest planet in the solar system. Mercury is the second, and it earns that with a body plan nothing else here has. So here is the arithmetic, worked all the way through, because it explains every world left in this film. Mercury has about half the mass of Mars. On its own, that halves the pull. But Mercury's surface sits 2,440 kilometers from its center, and Mars's sits 3,390. You are 28% closer in, and because the pull weakens with the square of the distance, being 28% closer multiplies it by about 1.9, half the mass, nearly double the closeness, 3.70 against Mars's 3.71. They cancel almost exactly, which means the thing your legs are responding to, standing on any world in this film, is not its size. It is how much is packed underneath you and how close the surface lets you get to it. On Mercury, you are standing on a thin shell of rock over an iron core that fills almost the entire planet. You are, as near as anywhere in the solar system, standing directly on the metal heart of a world, and that is why a place a third the width of Earth holds you down as firmly as somewhere half again its size. Chapter 2 asked what actually sets your weight. This is the answer, and it will not change again for the rest of this film. Now, what that arithmetic does not tell you. It gives you the pull at the surface, precisely, and it says nothing whatsoever about whether you could survive standing in it. Mercury's day settles that on its own. One full day-night cycle takes 176 Earth days, and the planet goes round the Sun in 88, so a single day on Mercury lasts 2 of its own years. That number is not an accident of a slow spin. Mercury turns exactly 3 times for every 2 trips around the Sun, a locked ratio, held in place by the Sun's pull on a planet this close. 3 rotations, 2 years. Work it through, and the sunrise to sunrise day comes out at 176 days every time. The ground reaches 430 degrees in that daylight. At night it falls to 180 below, not over a season, over 1 rotation, in the same place, on the same rock. And once again, the number nobody has. What 38% of Earth's gravity does to a human body across years. That is 3 chapters in a row where the honest answer is that the experiment has never been run. Stand there and the strangest thing would be the Sun. It is 3 times wider in that sky than the one you know, and it crawls. It would take weeks to cross. And because Mercury's orbit is stretched, and its spin and its year are locked into an odd ratio, there are places where the sun rises, stops, reverses, sets again, and then rises a second time. Your shadow would be sharp enough to cut, because there is no air to scatter light into it. And it would barely move all day, because the day is 3 months long. So why does the smallest planet in the solar system get its own chapter in a film about your body? Because it is the cleanest demonstration there is of the rule that governs everything left. 9 more worlds are coming, and not one of them will surprise you again in the way this one just did. You now know what to look at, and it is not the picture. It is what is underneath, and how close the surface lets you get to it. 30.2 kilograms on Mercury, 30.3 on Mars. A third of a width apart, and identical in the only way your legs would notice. You do not weigh what a world is. You weigh what is under you and how close you are allowed to stand. Of every world in this film, there is exactly one where your body would not notice much. Not the moon, where you cannot stop. Not Mars, where your legs would carry less than half of you. Here, stand on Venus and you would weigh 72 kilograms instead of 80, a tenth lighter. The kind of difference you would get from a hard week. Your legs would work. Your inner ear would agree with your eyes. Something in you would recognize the ground. And you would be dead in less time than it takes to describe what killed you. Everything you are about to see of that ground was photographed by 4 Soviet landers, and then never again. Venus is very nearly the same object as the Earth, 12,104 kilometers across, against our 12,756, 95% of our width, 82% of our mass. Rock, iron core, the same neighborhood of the solar system, formed out of the same material at the same time. Run those 2 numbers through the rule from the last chapter, how much is under you, how close you can stand, and Venus comes out at 8.87, 90% of Earth. There is nowhere else that close. Not one other surface in the solar system would let your body carry itself the way it does right now, and then everything else about it goes wrong at once. The ground is basalt plain, volcanic, wrinkled with ridges and dotted with structures that have no counterpart here. Almost all of what we know of that landscape comes from radar because you cannot see the surface from orbit at all. The cloud is total, permanent, and it never opens. Those clouds are sulfuric acid, not acid rain in the sense we mean it, the actual working fluid of the weather system, and the whole planet turns backwards. On Venus, the sun rises in the west, and it takes 117 Earth days to go from that sunrise to sunset. One rotation runs 243 days, while a year runs 225. The day is longer than the year, and the air does not turn with the planet. Venus's atmosphere races around it roughly once every 4 Earth days, while the solid body underneath takes 243. The whole cloud system laps the ground it sits on 60 times over in a single Venusian day. One more thing it does not have. Mercury, a fraction of this size, generates a magnetic field from the molten metal turning inside it. Venus, almost exactly Earth's size, almost certainly with a hot metal core of its own, generates nothing measurable. It turns too slowly to run the dynamo. Whatever is down there is not moving the way ours does. But none of that is what kills you, and neither is the heat, not first. Look at the edge of Venus and compare it with the edge of Mars. On Mars, the atmosphere was a hairline, a band so thin you had to be told it was there. Here it is a visible depth, a shell of gas thick enough to see as a thing in its own right. At the surface, that gas presses down at about 93 times the pressure of Earth's air at sea level. That is not weather. That is not even really an atmosphere in the way your lungs understand the word. Standing on Venus is, in NASA's own comparison, like standing more than 3,000 feet underwater. Call it *** the ocean of air ***. And we know what it is like down there because people put cameras in it. Between 1975 and 1982, the Soviet Union landed a series of machines on the surface of Venus. Venera 9 returned the first photograph ever taken from the surface of another planet. Venera 13 and 14 sent back color. They were built like submarines because that is the correct engineering problem. Titanium pressure vessels, pre-chilled before descent, and every one of them was on a clock from the moment it touched down. Venera 13 was designed to last about half an hour. It lasted a little over 2 hours, which remains the record, and in that time it photographed the ground around it, sampled the soil, and recorded the sound of wind on another planet. Then the heat got into it, and it stopped. There are fewer than a dozen usable images from the surface of Venus. All of them are more than 40 years old. Nobody has taken a photograph on that ground since 1982, and there is nothing currently there. So put the three surfaces of this act side by side, in the units your body would feel them in. Mars presses on you with 0.6% of the air you are breathing now, not enough to keep the water in your mouth liquid. Earth 1, Venus 93. 93 times, and it is 467 degrees, which is hotter than a domestic oven can reach, hot enough that lead on that ground would be a puddle. The pressure alone would kill you. The heat alone would kill you. The acid alone would kill you. You do not get to find out which one arrived first. And then there is the exception, which almost nobody mentions. Go up. 50 kilometers above that ground, inside the cloud deck. The pressure falls to about 1 atmosphere, and the temperature comes down into a range a human being can tolerate. Not comfortable, survivable. It is, by those two numbers alone, the most Earth-like place in the solar system outside the Earth, and it is 50 kilometers of thin air above the most lethal surface we know of. You would still need oxygen, and you would still need something the acid could not eat through. But you would not need a pressure suit. Nowhere else off this planet can you say that. And here is the shape of it, which you can only see with Mars sitting next to it. Mars very nearly gets your body right, and then fails because there is almost no air. Venus very nearly gets your body right, and then fails because there is far too much of it. The same organ, the same failure, opposite directions, two worlds either side of us, both landing within a few tens of % of Earth's pull, and both lethal for reasons that have nothing whatsoever to do with weight. Your legs are not what the universe is testing, which means it is worth being honest about how little we have actually seen. Everything anyone knows about standing on Venus comes from under 3 hours of total camera time, across 4 machines, more than 4 decades ago, at 4 locations on a planet the size of this one. The images are small, low in resolution, and shot through a lens that was already cooking. We have shown them to you at the size they exist. They have not been enlarged to fill this frame, because enlarging them would be inventing detail that nobody has. And once again, for the 4th chapter running, nobody can tell you what 90% of Earth's gravity does to a body over years. On Venus, that question does not even get to the front of the queue. If you could somehow stand there, protected, the strangeness would not be the heat. It would be that the air has weight. At 93 atmospheres, carbon dioxide stops behaving like a gas and starts behaving like a fluid. You would not walk through it so much as wade. Moving your arm would meet resistance. Sound would carry differently. Voices would drop in pitch and travel further. The light would be dim orange and come from no particular direction because it has been scattered through 50 kilometers of cloud before it reaches the ground. No shadows, no sun. Just a sky that glows evenly and does not change for 117 days. So of everywhere in this film, why is the one that feels most like home the one that kills fastest? Because weight was never the hard part. Every world we have visited so far has been within a factor of 6 of Earth's pull, and your body could probably learn to live with any of them. What it cannot learn to live with is what is sitting on top of the ground, whether there is too little of it or far too much. 72 kilograms, 90%, 95% of Earth's width in the next orbit in. Venus is the closest your body will ever come to being home. That is not a comfort. It is the measure of how little weight has to do with it. Every world in this film so far has taken something away from you. The moon took your ability to stop. Mars took the air, Mercury took the sky, Venus took everything at once in under 2 minutes. This one gives something back. On Titan you would weigh 11 kilograms, and the air there is 4 times thicker than the air in this room. Put those two numbers together and you get something that is true nowhere else we know of. Strap a pair of wings to your arms, run a few paces, and you would fly. 2 moons, 4/1000ths of a gravity apart, and one of them would kill you in a week. Flight is a straightforward argument between two quantities: how much air your wing can push down against how much weight that push has to hold up. On Earth you lose that argument badly. Air is thin, you are heavy, and no amount of flapping closes the gap, which is why every serious attempt at human-powered flight here has needed a wingspan wider than a bus. Titan changes both terms at once in the direction you want. The air at its surface is about 4 times denser than ours, so every wing beat moves far more of it, and you weigh 1/8 of what you weigh now. The argument stops being close, it stops being an argument, and it is a real place, not a thought experiment. Titan is bigger than the planet Mercury. It has a thick orange atmosphere of nitrogen, the same gas that makes up most of ours, with methane playing the part that water plays here. There is weather. There are clouds and rain and rivers that cut channels and lakes and seas standing on the surface, the only other world we know of where liquid pools in the open. The liquid is methane and ethane. The rain falls slowly, in fat drops, through air that is thick enough to hold it back, and the pressure at the surface is about 60% higher than Earth's. Not 93 times, not 0.6%. Half again the pressure you would feel a few meters underwater in a swimming pool. So what is wrong with it? The temperature. Titan sits at about 179 degrees below zero. The coldest temperature ever recorded on Earth is -89.2 at Vostok Station in Antarctica. Titan is another 90 degrees below that. Water there is not ice in the way you think of ice, it is bedrock. The hills are made of it. Water ice at that temperature has the mechanical properties of granite. You would not need a pressure suit. You would need to not freeze, and you would need something to breathe. Those are engineering problems of a completely different order to the ones Venus sets, and we know all of this because something landed there and looked. On the 14th of January, 2005, the Huygens probe separated from the Cassini spacecraft and descended through Titan's haze for 2.5 hours. Photographing as it fell, it touched down on a plain of rounded pebbles and kept transmitting. It is the most distant landing anyone has ever made. Those pictures are the only photographs ever taken from a surface in the outer solar system, and there has been nothing since. What the pictures showed was drainage, channels running down into a darker plane, the way rivers run into a basin here. Pebbles at the landing site rounded off, the way stones are rounded by being rolled along in a current. A landscape shaped by liquid, on a world where the liquid is not water and the temperature would freeze the air out of your lungs. Everything about it is familiar except the chemistry and the cold. And underneath all of it, well below the water ice bedrock, Titan is thought to hold a liquid water ocean of its own. 2 of the places in this chapter have oceans. Neither of them has one you can see. Here is the flying arithmetic, all the way through. The lift a wing makes goes up with the density of the air it beats against. Titan's air is about 4.3 times denser than ours, so the same wing moved the same way makes about 4.3 times the lift. The weight that lift has to carry is your mass multiplied by the local gravity. On Titan, that is 0.138 of what it is here. Divide one by the other. 4.3 over 0.138. The ratio of lift to weight comes out something like **30 times **, more favorable than on Earth. There is no other surface in the solar system where that number is anywhere near 1, let alone 30. And this is not an argument being made only in a documentary. NASA is building an aircraft for Titan. Not a lander with wheels, not a balloon, a rotorcraft with blades that will take off from the surface, fly to somewhere else on the moon, land, and do it again. It is called Dragonfly, and it is being built for exactly the reason this chapter is about. On Titan, flying is the easy way to get around. Nobody would propose that anywhere else. which makes Titan the only place we have found where a human body would be able to do something it cannot do on this planet. Not survive better, not move more easily, something genuinely new, leave the ground under its own power and stay up. Every other world in this film is a subtraction. The moon subtracts your footing, Mars subtracts the air, Venus subtracts the time. Titan is the one entry on the list that adds, and it charges 179 degrees below zero for the privilege. Now the correction, and it is the same correction Chapter 1 had to make about the moon. The arithmetic is for a body. It is not for a body in a suit. Whatever you are wearing on Titan would have to hold heat in against a 200-degree gradient, carry its own oxygen, and keep working in liquid methane. That is mass on your back and stiffness in every joint, exactly what turned a theoretical 3-meter lunar jump into a measured 42 centimeters. The flying is real physics. The flying in practice is an engineering question nobody has answered. And once again, the 5th chapter in a row, nobody can tell you what a 1/7 of a gravity does to a body over years. There is no data. There has never been anybody there. Now the other one, which weighs almost exactly the same and could not be more different. Europa, a moon of Jupiter, smaller than ours, and at its surface you would weigh 10.7 kilograms, 4/1000ths of a gravity below Titan. Your legs could not tell them apart. Under the ice there is an ocean of salt water, and NASA's own estimate is that it holds twice as much water as every ocean on Earth combined. On a moon a quarter of this planet's width, that ocean should not be liquid at all, this far from the sun. It stays liquid because Jupiter will not let the moon rest. Europa is pulled and released on every orbit, flexed like a piece of wire being bent back and forth, and the friction of that flexing heats it from the inside. The same force that keeps the water warm is the reason the surface is cracked from end to end. But there is no air, so nothing to fly in. The surface is fractured ice at well below -150, and Jupiter's radiation belts sweep across it constantly. The dose on that ground would kill an unprotected person in days rather than years. Europa Clipper launched in October 2024 to study it, and it will do so from orbit in passes. Because staying there is the problem, so the two lightest worlds in this film weigh the same and end up in completely different places. 11 kilograms and air you could fly in, 10.7 and radiation that would open your cells, which is the last thing weight has to teach you. It sets what your legs feel and nothing else, not whether you can breathe, not whether you can stand the cold, not whether the sky is trying to kill you. 4/100ths of a gravity apart. And one of them is a place you could imagine visiting. 4 worlds took something from you. This one hands something back and then asks for everything else. On Jupiter, you would weigh 188 kilograms, more than twice yourself. The weight of a large motorcycle carried on legs built for 80. That is the number everybody quotes, and there is something wrong with it. Not the arithmetic is fine. The problem is the word asterisk on asterisk. There is no on. Jupiter has no surface, no ground, nothing solid anywhere near the top, and that number is measured at a line somebody had to invent. 5 worlds in. This film runs out of places to stand. Every number in this film so far has been a fact about a surface. 13 kilograms on the moon, measured standing on regolith. 30 on Mars, on basalt. 72 on Venus, on rock nobody has photographed in 40 years. 11 on Titan, on a plane of pebbles a probe actually landed on. Each one is the answer to asterisk what happens when this body meets that ground asterisk. Jupiter does not have a ground. Not deep down, not anywhere. It is hydrogen and helium the whole way, gas at the top, thickening downward until the gas becomes liquid, and further down until the liquid starts conducting electricity like a metal. At no point is there a line you could stand on. What there is instead is weather, at a scale that does not translate. Bands of cloud running the whole way round, moving in opposite directions, shearing against each other in curls, and it is hundreds of kilometers across. Storms that have been photographed continuously for longer than anyone reading this has been alive. The largest of them is wider than this entire planet. The Great Red Spot is a single storm, turning anticlockwise, that people have been pointing telescopes at since the 1800s and quite possibly earlier. You could drop the Earth into it and have room left over. It has been shrinking for as long as anyone has measured it carefully, and nobody can say when it started or when it will stop. And the planet spins in 9 hours and 54 minutes. That is the fastest day in the solar system, on the largest object in it, a body 11 times wider than Earth, turning right round in less than half of one of our days. It is spinning so fast that it is visibly out of round, bulging at the equator. About 1,000 Earths would fit inside it. It holds more than twice the material of everything else orbiting the Sun put together. So where exactly do you take the reading? Somebody had to decide, because gravity depends on how far you are from the middle, and without a surface, there is no obvious distance to use. The convention is this: find the altitude where the pressure of Jupiter's atmosphere happens to equal the pressure of Earth's air at sea level. 1 bar, measure there, call it ***, the 1 bar line ***. It is not a place, nothing marks it, you could not photograph it. It is an agreement. Adopted because the planet offers nothing else, and every figure you have ever seen for Jupiter's gravity is quoted from it. And we know what is underneath because of the way a spacecraft falls. Juno has been swinging in over Jupiter's poles since 2016, dropping close to the cloud tops and then back out. Every pass, the planet's gravity tugs on it slightly unevenly, depending on how the mass inside is arranged, and those tugs shift the spacecraft's speed by amounts small enough to measure in millimeters per second. Track that precisely enough, over enough orbits, and the interior stops being a guess. Those same passes showed something at the poles nobody predicted. The cyclones up there are not scattered. They sit in a regular arrangement, 8 storms in a ring around a 9th at the North Pole, 5 around a 6th at the South, each hundreds of kilometers across, packed close enough to touch and holding the pattern for years without merging. Nothing on Earth does that. What Juno found was that the middle of Jupiter is not what anyone drew. The textbook picture was a small rocky core with layers stacked neatly on top. What the gravity measurements describe instead is what NASA's own summary calls a *** dilute or fuzzy core ***, heavy material spread out and mixed through the hydrogen above it, with, in their words, no clear separation from the metallic hydrogen around it. There is no boundary. The center of the largest object in the solar system does not have an edge. So follow the thing this film keeps asking and drop a body through it. At the 1 bar line you weigh 188 kilograms and you are falling because there is nothing to stop you. The temperature there is about 110 below. Downward, the pressure climbs, and so does the temperature. You pass through cloud, then thickening gas, then gas that is no longer really gas. Long before you reach anything that could be called a bottom. The pressure has crushed you and the heat has taken what is left, and the weight keeps rising the whole way because you are getting closer to the mass. The number in the readout was only ever true at one altitude, for one instant on the way past, which is where this film's question breaks. 5 chapters have asked what a world would do to a body standing on it. Jupiter cannot be asked that, because standing is not available. The one number we quote is a measurement taken at a line we invented, and past that line the answer is not a weight, it is a fall with no floor. And notice what has happened to the readout. On the moon it meant * what your legs carry *. Here it means * what you would weigh at the instant you passed an imaginary altitude, still accelerating *. Same units, completely different fact. And there is a second thing to be honest about, which is how much of this is inference. Nobody has been inside Jupiter. One probe was dropped into it in 1995, and it transmitted for under an hour before the pressure ended it, and it never got remotely deep. Everything below that is read out of gravity measurements and the physics of hydrogen under pressures we cannot make on Earth. The fuzzy core is the honest version of that. It is not a shape somebody drew and then confirmed. It is the arrangement that best explains how a spacecraft's speed changes as it goes past. And once again, the 6th chapter running, nobody can tell you what sustained 2.4 gravities does to a human body over hours. Brief high G is well studied. This is not brief, and nobody has been in it. If you could hover there, held up somehow, the strangest thing would not be the weight. It would be that there is no horizon in the way you mean it. The cloud curves away for tens of thousands of kilometers, and the bands run past you at speeds that would be a hurricane on any other world, and none of it is going anywhere you could walk to. Above the poles, there are aurorae hundreds of times more powerful than ours, driven by a magnetic field between 16 and 54 times Earth's strength, in a magnetosphere so large its tail streams out past the orbit of Saturn. The same field traps the radiation that makes Europa, from the chapter before this one, lethal to stand on. Everything about Jupiter is the solar system's largest version of itself, including the parts that would kill you. So this is where the first half of this film stops. 6 worlds, and your weight on them running from 11 kilograms to 188, a factor of 17, across places we have photographed, landed on, and in one case walked across. Every one of those numbers came from somewhere real. From here on, they do not. Everything left in this film is a planet nobody has photographed, orbiting a star nobody has visited, and every weight is calculated from a mass and a radius inferred from a dip in starlight. Every weight in this film has been a fact about a surface. Jupiter is where we ran out of surfaces and had to agree on a line instead. "40 light years from here, there is a planet where you would weigh 65 kilograms. Not 13, not 188, 65 against the 80 you are carrying now, a difference you would get from a bad fortnight. It is very slightly smaller than Earth and slightly lighter, and of everything outside this solar system, it is the closest match to the ground under your feet that anyone has found. And nothing about what would kill you there has anything to do with the planet. Nobody has photographed this world. Nobody ever has. Everything you are about to see of it is either a painting or a graph. Here is everything we actually know and how thin it is. 7 planets cross in front of that star, and every time one does, the star dims by a fraction we can measure. How deep the dip is tells you the planet's width. How the planets tug each other off schedule tells you their masses. That is it. 2 numbers from a flickering point of light. 0.692 Earth masses, 0.92 Earth radii. Divide the first by the square of the second, and you get 0.818. And everything this film has said about your body applies to that number as reliably as it applied to the moon. The system is nothing like ours. All 7 planets orbit closer to their star than Mercury does to the Sun. TRAPPIST-1e goes round in 6 days and 1 hour, at about 1/34th of the distance between us and our own star. The whole system would fit comfortably inside Mercury's orbit with room to spare, which means the planets are close to each other all the time. From the surface, the neighboring worlds would not be points of light. They would be disks, some of them larger in that sky than our moon is in ours, moving visibly night after night. And the orbit is almost perfectly circular. Eccentricity 0.01. Whatever else is unstable there, the distance is not. So what is wrong with it? Not the planet. Asterisk the star. Asterisk TRAPPIST-1 is an M-type red dwarf, small, cool, and dim enough that its habitable zone sits almost on top of it. That is the only reason a planet at 1/34th of Earth's orbital distance is not molten, and it is small in a way that is hard to hold. TRAPPIST-1 has about 9% of the Sun's mass, and it is barely larger across than Jupiter. A star the size of a planet, with 7 worlds packed around it inside the space Mercury has to itself. But being that close to any star has consequences, and red dwarfs have a specific problem: they flare. Violently and often, throughout lives measured in trillions of years. That last part is not a slip. A star this small burns its fuel so slowly that it will still be shining when the sun has been a cold white ember for 100 times the age of the universe. Whatever happens on those 7 planets has almost all of time left to happen in. A planet parked that near gets the full weight of it. Call it ***, the wrong sun ***. We found it by watching the star blink. In 2017, a set of small telescopes and then Spitzer confirmed 7 worlds crossing that one point of light in a chain, the largest set of Earth-sized planets ever found around a single star. Everything after that has been inference, stacked on inference. The masses come from the way the planets pull each other slightly ahead of and behind schedule. That works because the 7 are locked into a chain. Their orbital periods sit at near whole number ratios, so the same planets line up in the same arrangements over and over, and the tugs accumulate into something measurable instead of averaging away. It is the longest such chain known. Webb has since been pointed at them to look for atmospheres. Nobody has resolved one of these planets as an object. They are still, and will remain for a long time, a pattern in a light curve. What makes this one matter is where it sits in the chain. Of the 7, TRAPPIST-1e is the one that lands squarely in the range where liquid water is possible, and it is the one whose density best matches rock rather than ice or gas. It is, on the numbers, the most Earth-like planet in the most Earth-like system anybody has found. And the numbers are 2, a width from how much light it blocks, and a mass from how it disturbs its neighbors. Put it on the scale this film has been building: 13 kilograms on the Moon, 30 on Mars and Mercury, 72 on Venus, 11 on Titan, 188 at Jupiter's 1-bar line, 65 here. Your legs would carry 4/5 of what they carry now. Your heart would move blood against 4/5 of the pull it fights every second of your life. Of every number in this film, this is the one your body would have the least to say about, and it is orbiting a star that throws flares at it from 1/34 of the distance we sit from ours. And here is the pattern, which has been running since the first chapter and is worth saying out loud now. The Moon, the gravity was survivable. What got you was that you could not stop. Mars, the gravity was almost right. What got you was that there was no air. Venus, the gravity was nearly Earth's. What got you was 93 atmospheres of it. Titan, the gravity let you fly. What got you was 179 below. Jupiter, there was no ground to have gravity on. 7 worlds now, and not once has the weight been the thing that killed you. Here it is a star that flares. There is nothing wrong with the planet at all. Now the size of what we do not know, because it is most of it. Nobody has confirmed whether TRAPPIST-1e has an atmosphere. Without one, the flares reach the ground and the surface is sterilized. With a thick one, it might be shielded. Webb has looked. The answer is not in yet. What Webb has already reported is not encouraging. It examined the 2 innermost planets of this system and found no sign of a thick atmosphere on either bare rock, as far as the instrument could tell. Those 2 sit closer to the star and take more punishment, so it does not settle the question for this one. But it is the first hard evidence in, and it went the wrong way. Nobody has confirmed it is tidally locked, though a planet that close to a star that small is expected to be one face in permanent daylight, one in permanent night, and a ring of perpetual dusk between them where the temperature might work. And the gravity figure, the one solid thing in this chapter, rests on a mass derived from how 7 planets tug on each other. It is a good measurement. It is not a landing. 7 chapters. And the honest answer keeps being the same. The number is real, and standing there is a question nobody has asked a body. If the atmosphere is there and you could stand in it, the strangeness would start with the light. A red dwarf puts out most of its energy in the infrared. The daylight would be dim and deeply red, closer to the last 20 minutes of a sunset here than to noon, and it would never move because the same face is always turned toward it. No sunrise, no dusk. One fixed red sun sitting in one fixed place in the sky for as long as you stayed, and the other planets crossing behind it, big as coins held at arm's length, some of them showing phases like our moon. Your body would weigh 65 kilograms and feel almost at home. Nothing else would. So this is the first world in this film that nobody has ever seen. 6 chapters of photographs, of landings, of a probe on a plane of pebbles, and now a number pulled out of a flicker. 40 light-years away, describing a place where your body would be more comfortable than it would be anywhere else off this planet. 65 kilograms, 4/5 of you, on a world that might be sterilized by its own sun. The planet is not the problem. It never has been. 7 worlds in this film could hold your body, and every one of them is trying to kill you with something else. Put a set of bathroom scales down on a planet 49 light-years from here and step onto them. They read 94 kilograms. You weigh 80, 14 kilograms more, a heavy winter coat with a full rucksack underneath it. You would notice it on the stairs. You would barely notice it anywhere else. Now the part that should not fit. The planet under those scales is nearly twice the mass of Earth. Not twice the width. Twice the mass. Almost 2 entire Earths of rock and iron. Pulling at you from beneath your feet. Twice the mass. 14 kilograms. By the end of this chapter you will know exactly where the rest of it went. The rule you have carried since school is simple and very nearly right. Mass makes gravity. Put more mass underneath something and it is pulled down harder. It is why you weigh 6 times less on the moon. The moon is a small thing, and there is very little of it to do the pulling. So a planet with 2 Earths inside it ought to be punishing. A world where standing is work and falling is serious. Every story you have read about a heavy world is built on that assumption. It is wrong, and the reason it is wrong is the single most useful thing in this entire film. The planet is called LHS 1140c. Its star sits in the constellation of Cetus, a red dwarf, catalogued as LHS 1140, an M4.5 dwarf, 3096 degrees at its surface, a little under 1/5 of the mass of our Sun and a little over 1/5 of its width. Small, cool, and unusually quiet. To picture that star, stop thinking of the Sun. Its radius is 1/5 of the Sun's, roughly twice the width of Jupiter. A star barely 2 Jupiters across, burning at half our Sun's temperature, throwing out a deep red light. And here is the thing that separates this system from the last one. In the previous chapter, the planet was fine, and the star was trying to kill it, a red dwarf that flares violently and often. LHS 1140 is reported to be the opposite kind of star. Old, slowly turning, and quiet. Not proven harmless, nothing at this range is, but quiet enough that astronomers keep coming back to it. LHS 1140c goes around it in 3 3/4 days. 3.778 to be exact. Your working week is longer than that planet's year. It orbits at 1/37th of the distance between the Earth and the Sun, close enough that the star fills a great slab of its sky and never sets, and it goes round almost perfectly circular. An eccentricity of 0.05, near enough a true circle that it takes the same heat from the same distance every day of its year. No seasons, no long cold arc away from the fire, just the same red afternoon. Repeating, here are the 2 numbers that matter. Both of them are measured. Mass, 1.91 times the Earth. Radius, 1.272 times the Earth, nearly double the mass, only a quarter again the width. Put those through the arithmetic, mass divided by radius squared, and the gravity at the surface comes out at 1.18 times our own. 1.18, not 2, not 1.5. That is the math. It is worth stopping on why we can say that at all. Most worlds in this film hand us one number or the other. A planet that crosses in front of its star dims it, and the depth of that dip tells you how wide the planet is. A planet that pulls its star about as it orbits makes the starlight shift back and forth, and the size of that shift tells you how heavy it is. You need both to get a weight. Width alone gives you a shape. Mass alone gives you a pull with nothing to stand on. LHS 1140c does both. It crosses and it tugs. That is why this chapter can put a real figure on your bathroom scales, and why 5 of the 14 worlds in this film cannot. We found it in 2018. It has been giving up both numbers ever since, and it is not alone. Further out, on a 24-day orbit, sits a second world, bigger, heavier, and cold enough that the arithmetic puts it at 53 degrees below freezing. That one sits in the zone where water could stay liquid. It is the world we finish this act on. So where did the missing gravity go? Into the radius. Gravity does not care only about how much is underneath you, it cares about how far you are from the middle of it. Stack up nearly 2 Earths of rock, and that rock takes up room. The surface swells outward, and when you stand on that swollen surface, you are standing further from the center of a world than you have ever stood in your life. The mass pulls harder. The extra distance holds you further away. The two of them very nearly cancel. That is the super Earth discount, almost double the planet for 18% of the price, and you can watch it hold right across this film. LHS 1140c is 1.91 Earth masses and gives you 1.18 gravities. Its neighbor, the world we come to at the end of this act, is 5.6 Earth masses, nearly 3 times heavier again. It gives you 1.87, triple the mass, 60% more weight. Mass climbs like a staircase, weight climbs like a ramp. Now the thing this chapter must not overstate, you will find LHS 1140c listed at 422 Kelvin, 149 degrees Celsius, hotter than boiling water. It is the number that decides whether anything could live there, and it is quoted everywhere. Nobody has measured it. That figure is calculated. You take the star's output, you take the planet's distance, you assume a reflectivity, and this is the part that matters. You assume the planet has no atmosphere whatsoever. Wrap it in air and the real number climbs. Give it a bright, reflective surface and the real number falls. So the honest sentence is this. On the arithmetic, and only if it is bare, LHS 1140c should sit somewhere around 150 degrees. We know what that planet weighs far better than we know how hot it is. Stand there anyway for a moment. 94 kilograms of you on rock very slightly less dense than the rock at home. 5.1 grams per cubic centimeter against Earth's 5.51. Rock and iron, put together in roughly the proportions you are used to. It would look like ground. It would feel like ground. The red dwarf hangs enormous and unmoving. Your shadow does not travel. Your legs carry that extra 14 kilograms and complain about it on any slope. Standing still is easy. Standing up 100 times a day is the thing you would feel. Your jump is shorter by about 1/6. Your heart works a little harder to lift the same blood the same distance. Your body would adapt. That is the point. That is the entire point. So let us do the sum out loud, one step at a time, because it is the sum this whole film runs on. Take the mass. 1.91. Take the radius. 1.272. Square the radius and you get 1.62. Divide 1.91 by 1.62, 1.18. Multiply that by your 80 kilograms, 94.4, 4 steps, 2 measured numbers, not one opinion anywhere inside it. That is how much of you would arrive on a world nearly twice the mass of the one you were built on. Voyager 1, still moving at 17 kilometers every second, would need close to 900,000 years to reach it. And what would be waiting after 900,000 years is a 14-kilogram inconvenience. 14 kilograms, that is what very nearly doubling a planet buys you. Not a crushing weight, not a broken body, a heavy coat, a rucksack, and slightly harder work on the stairs. Everything that would genuinely stop you there is something else. The heat, if it is bare. The star, a 37th of the way out and never setting. The 3 3/4 day year. 8 worlds now, not one of them has killed you with its gravity. It is never the weight, it is always what the weight is standing in. There is a world 124 light years from here where you would weigh 127 kilograms, 47 kilograms more than you weigh now. Not a coat and a rucksack this time. A second adult on your back permanently. It is the most famous planet in this film. It is the one that puts headlines about life beyond Earth on the front pages. And there is a serious possibility that there is nothing there to stand on at all. That number, 127 kilograms, is real arithmetic. Whether it means anything is what this chapter is about. Weigh a world, measure how wide it is, and you can work out something far more useful than either. How tightly it is packed. Divide the mass by the volume and you get density. Earth comes out at 5.51 grams for every cubic centimeter. That is the number you get when you build a planet out of rock and iron. Iron in the middle, rock on top. Density is the closest thing we have to opening a planet up and looking inside it. You cannot see through a world from 124 light years away. But you can weigh it, and you can measure it, and the answer tells you what it is not. The planet is called K218b. It orbits an M dwarf, a red star about a third the mass of our Sun and a little over 4/10 of its width, with a surface at 3,457 degrees. K218b goes round it once every 32.94 days, at about a seventh of the distance between the Earth and the Sun. And at that distance, around that star, the arithmetic gives an equilibrium temperature of 284 Kelvin, 11 degrees Celsius, a mild spring afternoon. That is why this planet is famous. Of everything we have found out there, it is one of the very few where the temperature you calculate is a temperature you could stand in, although that 11 degrees is an average and the orbit is not a circle. Its eccentricity is 0.2, noticeably stretched. Last chapter's world took the same heat from the same distance every day of its year. This one does not. It swings closer and further, and whatever weather exists, there has a season built into it. Now weigh it. 8.92 times the mass of the Earth, nearly 9 Earths, and measure it. 2.37 times the Earth's radius, 9 Earths of material in a ball only a little over twice as wide. That ought to be the densest thing in this film. Squeeze 9 Earths into that volume and you would expect rock crushed harder than rock has ever been crushed. So do the division. 8.92 divided by 2.37 cubed. It comes out at about 3.7 grams per cubic centimeter. Earth is 5.51. It is lighter, liter for liter, than the ground you are standing on, 9 Earths of mass and less dense than Earth. Rock cannot do that. So what is it made of? We know its width because it crosses in front of its star and blocks a fraction of the light. We know its mass because it pulls the star about as it goes. Put those together and you have the density, and the density rules things out. You cannot build a 9 Earth planet that comes out at 3.7 grams per cubic centimeter from rock and iron alone. There has to be something light in there, and a great deal of it. Water, ice, or an enormous atmosphere of hydrogen sitting on top of whatever the core turns out to be. And there is a third kind of measurement, which is the reason this planet is in the news rather than in a catalogue. When a planet crosses its star, a thin sliver of starlight passes through the very edge of its atmosphere on the way to us. Whatever is in that atmosphere absorbs particular colors out of that light, split it up afterwards, and the missing colors tell you which molecules the light passed through. We are not photographing the air on that planet. We are reading the gaps in a rainbow. Some sense of how far away this is being read from. Voyager 1, the most distant object we have ever built, is still moving outward at 17 kilometers a second. At that speed, it would reach K218b in about 2.2 million years. Everything we know about that planet, we know from a smear of light that crossed that distance and fell into a mirror. K218b was found in 2015 by transit. In 2019, Hubble observations were reported to show water vapor in its atmosphere, the first time that had been claimed for a planet in the temperate zone of its star. In 2023, the James Webb Space Telescope looked, and the published spectrum showed methane and carbon dioxide. That spectrum is on your screen now. It is not an illustration. Those wobbles are the data, and the shaded blocks mark the molecules those wobbles correspond to. There is a third label on that figure. We will come back to it. Here is the sum this whole film runs on. Mass, 8.92. Radius, 2.37. Square the radius and you get 5.62. Divide one by the other, 1.59. Multiply by your 80 kilograms, 127. Every step of that is honest. Both inputs are measured. The arithmetic is only arithmetic, and it may be describing a place that does not exist. Because if that planet is what its density suggests, a deep envelope of hydrogen over water, or over ice, or over an ocean nobody has ever seen, then there is no surface for 1.59 gravities to press you onto. You would not arrive on K218b. You would arrive at it and keep going. The pressure would rise around you and the temperature with it, and at no point would there be a flaw. The number is real, the flaw is not. And now the label we skipped, printed on that same published spectrum twice, is an abbreviation, DMS, dimethyl sulfide, on Earth. Almost all of it is made by living things, largely by plankton in the sea. That is why this planet was on the front pages. It has not been confirmed. The signal is weak. Independent teams have gone back to the same observations and disagreed about whether it is there at all, and it sits well below the confidence any of them would require to call something a discovery. The label on that figure marks where a possible signal was reported. It does not mark a molecule we know is there. Methane and carbon dioxide are different. Those are on the spectrum, and they are the strongest evidence we have ever had about the air of a temperate world. Dimethyl sulfide is a maybe. It is a careful, interesting, contested maybe, and this film is not going to sell it to you as anything else. Nobody has seen a surface. Nobody has established a biosignature. What we have is a density, a temperature, and 3 molecules, of which 2 are solid. So stand there anyway and notice that you cannot. 127 kilograms of you in a place where standing has nothing to attach itself to. Above the cloud tops, 11 degrees is a real number, and the light is red and dim and comes from one side. Below them, the hydrogen thickens. There is no shoreline, no rock, no moment where the falling stops and the standing starts. Your legs, which have carried you every day of your life, would have nothing to do. 47 kilograms more than you weigh now. One rung further up than the last chapter, LHS 1140C gave you 1.18 gravities and 94 kilograms. This one gives you 1.59 and 127, 2 worlds and 33 kilograms between them. On the moon there was too little of it. On Jupiter there was no ground to have it on. Here there are 9 Earths of mass, a temperature you could survive in, and quite possibly nothing at all underneath. 9 worlds now, not one of them has killed you with its gravity. The weight was never the problem. Somewhere under all of it, there has to be something to stand on, and that, not the number, is what the rest of this film is about. Stand on this one and the scales read 149.7 kilograms. You weigh 80, not a heavy coat, not a rucksack, not a second person you could put down, very nearly a second body fastened to yours and never coming off. This is the heaviest honest number in this film, and of all 14 worlds in it, this is the best one we have found. Both of those things are true at once, and that is what this chapter is about. Last chapter ended on a world that may have no ground at all. 9 Earths of mass, and a density so low that rock could not explain it, a number that described a surface nobody can be sure exists. So before anything else, ask the only question that matters. Is there a flaw? Weigh it. 5.6 times the mass of the Earth. Measure it. 1.73 times the Earth's radius. Divide the mass by the volume, the same sum as last time. And this world comes out at 5.96 grams for every cubic centimeter. Earth is 5.51. It is denser than the ground you are standing on, denser than the planet that made you. There is no thick envelope of hydrogen here, no deep ocean of uncertainty, nothing light padding out the volume. It is stone and iron packed harder than home. There is a flaw. Whatever else that world is, you could stand on it. The planet is called LHS 1140b, and you have already met its star. 2 chapters ago we stood on LHS 1140c, the inner world, the 3 3/4 day year, the one that cost you 14 kilograms. This is the other planet in that system, the outer one, the same small quiet red dwarf, 3096 degrees at its surface, barely 2 Jupiters across. This one takes 24 3/4 days to go round, at 9/100ths of the distance between the Earth and the Sun. Its orbit is very nearly a circle, an eccentricity of 0.043, so it takes the same light from the same distance all year, and at that distance, the arithmetic puts it at 226 Kelvin, 47 degrees below freezing. Cold. But that is Antarctic cold, not Neptune cold. It sits inside the band where water can be liquid, if there is enough air above it to hold the pressure. And that same number, on a world with no atmosphere, is simply what the sunlight allows. Remember to hold that lightly. Like every temperature in this film, it is calculated, not measured. Nobody has put a thermometer on this planet, and nobody will. There is a reason astronomers keep coming back to this particular star, and it is worth saying plainly, because it is rare for all of it to line up at once. The star is quiet, old, slowly turning, not the kind that throws flares at whatever orbits it, which is exactly what made the previous chapter's world so precarious. It is close, at under 50 light years. It has 2 planets we know of, and both of them cross in front of it from where we sit, which is the only geometry that lets us measure a width at all. And one of those 2 sits in the temperate band. Quiet star, near neighbor, transiting geometry, a world in the right place. Take any one of those away, and this chapter could not have been written. We found it in 2017. It crosses in front of its star, so we have its width. It pulls its star about, so we have its mass. Both numbers measured, both published, and this time something else as well. The archive lists a density of 5.9 grams per cubic centimeter. Our own division of its mass by its volume gave 5.96. Those agree to about 1%. That sounds like a small thing. It is not. Last chapter, the same 2 numbers disagreed by more than 10%, because catalogs are stitched together from different papers and the pieces do not always match. Here they match. When the arithmetic and the archive land on the same answer, you are allowed to lean on it a little harder. So put the 3 worlds of this act side by side. LHS 1140C, 1.18 gravities, 94 kilograms, K218b, 1.59, 127, and this one, 1.87, 149.7. Each step up is bigger than the last, and the ladder is not steep because the planets are wildly different. It is steep because we started at the bottom. Now the turn. Everything that has stopped you so far in this film has been something other than the weight. Airlessness on the Moon, pressure on Venus, cold on Titan, a missing surface on Jupiter, and possibly on K218b. A flaring star at TRAPPIST-1. Here none of that applies. The star is old and slow and quiet, the calm kind, not the kind that throws flares at whatever orbits it. The orbit is circular. The temperature is survivable with a coat and a sealed room. The ground is real, and it is rock, and it is under your feet. This is the best case, and on the best case you weigh 149.7 kilograms. For the first time in 10 chapters, the gravity is the hard part, so be exact about what that means and where the exactness stops. What we can compute properly. 3 things, all of them arithmetic. Take the jump. On Earth, a standing jump lifts your center of mass something like half a meter. Gravity that is 1.87 times stronger pulls that down to about 27 centimeters. Not a leap, a hop. Take walking. There is a speed at which walking stops being efficient and running takes over, and it scales with the square root of gravity. Yours would drop by around a quarter. You would break into a run sooner than you ever have, and running would cost more than it ever has. And take the smallest one, which is the one that would actually wear you down. Lifting 80 kilograms out of a chair is work. Lifting 150 is nearly twice that work, 100 times a day for the rest of your life. What we cannot compute, we should not pretend to. Whether your bones would thicken, whether your heart would enlarge, whether a child born and raised on that surface would grow up shorter and denser and stronger than anyone here. Those are guesses shaped by what happens to bodies under load on Earth, stretched across a lifetime nobody has lived. They are worth saying out loud. They are not worth stating as fact. Stand there then and be honest about it. The red dwarf is small and low and dim and does not move. The rock underfoot is darker and heavier than the rock at home. Your chest is doing more work at rest than it has ever done. Nothing about it is quick. Everything is possible and everything costs more. You would not fall over. You would not be crushed. Nothing dramatic would happen to you at all. You would simply be tired, in a way that never quite lifts and never quite resolves, on the most Earth-like world anyone has ever found. 49 light years. It is worth stopping on what that means, because close is doing a great deal of work in that sentence. Voyager 1 is the furthest thing our species has ever built. It has been flying for nearly 50 years, and it is still moving outward at 17 kilometers every second. At that speed, it would need about 860,000 years to reach this planet. 860,000 years ago, our species did not exist. That is the distance to the nearest world in this film where you could stand on real ground under a quiet star. 10 worlds now. The moon gave you too little gravity. Jupiter gave you nowhere to put it. K218b gave you a number without a floor to stand on. And here, at last, is a world where the arithmetic is clean, the ground is real, the star is quiet, and the weight is the thing you would notice every hour you were awake. It still is not what kills you, but for the first time, it is what you would feel. And that is where the measured worlds run out, because the next four cannot even tell you this much. For 10 chapters, this film has put a number on the scales. The Moon, 13 kilograms, Mars, 30, Jupiter, 188. 9 worlds after that, each one measured, each one divided out, each one honest. This chapter cannot do it, not because the planet is strange, because of one empty field in a catalogue. It is called Kepler 452b, and when it was announced in 2015, it was described everywhere as Earth's cousin. That description was not invented by journalists. It came from the orbit, and the orbit really is remarkable. Start with its star, a G2 dwarf. That is our sun's own classification, 5,757 degrees at the surface, almost exactly one solar mass. Not a red dwarf, not a flare star. The same kind of ordinary yellow star we happen to be sitting next to. Then, the distance. 1.046 times the distance from the Earth to the Sun. 4% further out. That is a rounding error on an astronomical scale. Then the year, 384.8 days. Ours is 365, 5% longer. Same kind of star, same distance, nearly the same year. Of everything found up to that point, nothing had ever matched Earth's situation so closely. And there is one more thing, which is the part that should stop you. That star is 6 billion years old. Ours is 4.5. Kepler 452 is what our sun will be in another 1.5 billion years, slightly larger, slightly brighter, working through the slow brightening that every star of this type goes through. So if that planet has an ocean, it is an ocean that has been sitting under a strengthening sun for longer than the Earth has existed. Whatever happens to a world like ours when its star ages, that world has already had it happen. That is not a small thought. Every star of this kind gets brighter as it burns through its hydrogen. Ours has gained roughly 30% since the Earth formed, and it is still climbing. There is a point, somewhere ahead of us, where the oceans start losing water to space faster than the planet can hold it. Kepler 452b is 1.5 billion years further along that road than we are. It is either the best available picture of where the Earth is going, or the best available picture of what that journey does to a world. Nobody can say which, because the one measurement that would tell us what is left of its atmosphere is far beyond anything we can do at that distance. Now the empty field, we know how wide it is, 1.63 times the radius of the Earth, 63% wider. That number comes from the transit the planet crosses in front of its star. The starlight dips by a precise fraction, and the depth of that dip is the planet's width. It is a clean measurement. We do not know what it weighs, not approximately, not roughly, not within a factor of 2, at all. The mass column in the catalogue is simply empty. To weigh a planet, you have to watch its star move. The planet pulls, the star swings, and the starlight shifts color by a few parts in 100 million. It is a delicate measurement, and it needs a bright star. Kepler 452 is 1,799 light-years away. At that distance, the star is far too faint for it. The instruments that weigh planets are working on stars 100 times closer. So we have a width, and we have nothing to put inside it. And width alone is not a weight. It is worth understanding why this planet is so far away, because it was not an accident. The Kepler telescope did not sweep the sky. It stared at one single patch, about the size of your hand held at arm's length, for 4 years without looking away. To catch a planet crossing its star, you have to be watching at the exact moment it crosses, and to catch one on a year-long orbit, you have to be watching for years. So Kepler picked a patch, held still, and monitored 150,000 stars at once. That patch happens to be deep. Most of those stars are hundreds or thousands of light years off. Kepler was built to answer how common planets like this are, not to study any particular one. It counted. It was never designed to weigh. Here is exactly how much that matters, because it is easy to assume the gap is small. Suppose it is rock, packed like Earth. Then its mass would be its radius cubed, 4.33 times the Earth. Divide that by the radius squared, and you get 1.63 gravities. An 80-kilogram person weighs 130. Now suppose it is not. Suppose it holds more water or a thicker atmosphere and comes out at half Earth's density, which is entirely ordinary for a planet this size. Then the mass is 2.17 and the gravity is 0.81. 0.81. You would weigh 65 kilograms, less than you do now. Same planet, same measured width. And the answer swings from 130 kilograms to 65, depending on a single thing nobody has measured. And those two worlds are not variations on a theme. They are different places to be a body. At 1.63 gravities, you are carrying 50 extra kilograms permanently. Standing up is heavy work, a jump is a hop, and your heart runs harder than it ever has at rest, the world we finished the last chapter on, and then some. At 0.81, you are 15 kilograms lighter than you are right now. You would move the way you move on a good day every day. Your stride would lengthen. You would go upstairs and notice you had not been trying. Same planet. One of those is true and the other is not, and there is no measurement anywhere that says which. So this chapter will not give you a number. It would be very easy to pick the rocky assumption, state 1.63, add the word probably, and nobody watching would object. 10 chapters of real arithmetic have earned exactly enough trust to get away with it. That is precisely why it is not going to happen. A number invented here would be indistinguishable to you from the 10 that were real, and then none of them would mean anything. What can honestly be said is this: it is 63% wider than Earth. It goes round a star like ours at nearly our distance in nearly our year. Its equilibrium temperature works out at 265 Kelvin, about 8 degrees below freezing, and like every temperature in this film, that is calculated, not measured. Everything else is a guess wearing a decimal point, and the mass is only the first missing thing. Nobody knows whether it has an atmosphere or what that atmosphere is made of. Nobody knows whether it turns quickly or slowly, or whether it has a magnetic field, or a moon, or water. The catalog row for this planet is mostly empty space, and the few entries in it describe an orbit rather than a world. We know where it is, we know how big it is, we know what kind of star it goes round and how long it takes. Everything a person would actually want to know about standing there is unmeasured. Stand there, if you can call it standing. You do not know if the ground would push back a little harder than home or a little softer. You do not know if there is ground. The star overhead would look almost exactly like the sun does from your window, the same color, nearly the same size, a little brighter, and that familiarity is the most misleading thing about the place. Voyager 1, at 17 kilometers a second, would need about 32 million years to get there. 32 million years ago, there were no apes anywhere on Earth. 11 worlds now, and the pattern breaks. And the honest tally has changed. 10 of them told you what you would weigh. This one told you that the instrument that measures weight has a range, and this planet is outside it. The weight was never what stopped you. Out here, at 1800 light years, what stops you is that nobody has weighed it at all, and the next 2 chapters are worse. In 2011, a telescope confirmed the first planet it had ever found sitting in a habitable zone, and the news went round the world. It is called Kepler 22b. It is 635 light-years away. It goes round a star slightly smaller and slightly cooler than our Sun, once every 289 days, at 8/10 of the distance from the Earth to the Sun. The arithmetic puts it at 279 Kelvin, 6 degrees above freezing. That is a real result, and it deserved the coverage. It was the moment the search stopped being theoretical. Before that announcement, habitable zones were a calculation, a band you could draw around any star on paper, where the arithmetic said liquid water would be stable. Plenty of planets had been found by then, but they were hot Jupiters and scorched rock, orbiting in days. Nobody had confirmed anything sitting in the band itself. Kepler 22b was the first. Whatever else is uncertain about it, that part is history and it does not move. 15 years later, here is what we can tell you about standing on it. At most 165 kilograms, not 165, at most. Those two sentences describe completely different situations, and only one of them is true. That phrase is the entire chapter, and it is worth being precise about what it means, because it is a stranger kind of ignorance than the last one. Last chapter, the mass field was empty. Nothing had been measured, so the answer could go either way, a heavy rock world or a light hazy one, and no way to choose. This time there is a number in the catalogue, 9.1 Earth masses, but sitting next to it is a small flag that changes everything. It is a limit. 9.1 is not what this planet weighs. It is the most it could possibly weigh. Here is where that comes from. To weigh a planet, you watch its star wobble. Astronomers watched this one carefully for years, and the star did not visibly move. A non-detection is not nothing. It tells you the planet cannot be heavy, because a heavy planet would have shown up. So you can draw a ceiling. Anything above 9.1 Earth masses would have made the star swing enough to see. What a non-detection cannot do is tell you where under that ceiling the truth sits. It is worth being clear about which measurement here is solid, because one of them genuinely is. When this planet passes in front of its star, the light we receive drops. Not by much. For a world this size against a star this size, the dip is a fraction of a percent. But it is a clean, repeatable geometric fact. The fraction of light removed is the fraction of the star's disk the planet covers. Measure the depth of the dip, know the size of the star, and the planet's width falls straight out of it. That is why width is the one thing we usually have. It needs only patience and a steady detector. Mass needs the star to move, and stars are very heavy and very far away. So work it through. We know the width, 2.1 times the radius of the Earth, measured cleanly from the transit. Take the ceiling mass, divide by the radius squared, and you get 2.06 gravities. 80 kilograms of you becomes 165. That is the heaviest you could possibly be there. Now halve the mass. 4.5 Earths, which is entirely allowed by the data, nothing rules it out. The gravity falls to 1.03. You would weigh 83 kilograms, 3 kilograms more than you do at home. Quarter it, 2.25 Earths, also allowed by everything anyone has measured. 0.52 gravities, 41 kilograms. You would weigh half what you weigh now. Your stride would carry you further than you meant it to. A dropped object would take noticeably longer to reach the floor, and everything you did would feel very slightly like something remembered from a dream. 165, or 83, or 41. Every one of those is consistent with everything anyone has ever measured about this planet. And notice what is missing from that list. There is no floor. A ceiling tells you how high a number cannot go. It says nothing whatsoever about how low it can be. It would be easy to hear all this as a complaint, and it is not one. A ceiling is a real scientific result. It rules out an entire class of planet. This cannot be a Neptune. It cannot be a gas giant. It cannot be any of the heavy things it might have been. That is genuine knowledge, obtained by careful people looking hard and honestly reporting that they saw nothing. The failure would be to take that ceiling and quietly report it as a value, because a number without a qualifier travels further than one with. Which is why this chapter is stranger than the last. Kepler 452b at least had symmetry, a range with two ends, and the truth somewhere between them. Here there is one end and an open drop underneath it, There is a second limit flag on this planet, and it is worth showing you because this film very nearly stated it as a fact. The catalogue lists an orbital eccentricity of 0.72, taken at face value that would be a dramatic orbit, swinging far in and far out, with the temperature lurching through every year. It would make a very good paragraph. It is also a limit, at most 0.72. And 6 other published measurements of this same planet give the eccentricity as 0 a circle. So the honest sentence is that we do not know the shape of its year either. It might be a clean circle. It might be a long ellipse. The data allows both, and the number that looked like a fact was a ceiling wearing a decimal point. That is 2 of this planet's headline figures that are not figures at all. Both of them would have read perfectly well in a script. Neither of them is a measurement. And there is a third thing, which is the part that should make you cautious about the whole idea of standing there. It is 2.1 times the radius of Earth. That sounds close. It is not. At that size, planets very often turn out not to be rocky, big enough to have held on to a thick envelope of gas when they formed, and never to have lost it. We saw one already in this film, and it may have had no surface at all. Nobody has established what Kepler-22b is made of. A calculated temperature of 6 degrees describes the top of whatever is there, which may be cloud, hundreds of kilometers above anything solid, if anything solid exists. So what does this world actually give us? It gives us a width, measured properly. It gives us an orbit and a year, both clean. It gives us a star we understand well, because it is nearly a copy of our own, 5,596 degrees at the surface. About 6/7 of the Sun's mass, a little smaller across. Not a red dwarf with its flares and its tidal locking and its unanswered questions. An ordinary yellow star of the kind we have studied at close range for centuries, behaving in ways we can predict. And it gives us a ceiling on a mass, which is a real result, honestly obtained, and far less than it sounds like. Everything a person would want to know, the ground, the air, the weight. Whether there is a surface to have weather on is unmeasured. Stand there then with the appropriate uncertainty. You might be crushed to 165 kilograms. You might be floating along at 41. You might not be standing at all, because there may be nothing under you but deepening cloud. Voyager 1, at 17 kilometers a second, would take about 11 million years to arrive and find out. It has been flying for 50 of them. 12 worlds now. And the ground is getting thinner under the arithmetic. The first 10 told you exactly what you would weigh. The 11th could not tell you at all. This one can tell you only what you would not exceed. The weight was never what stopped you. Out here, the thing that stops you is that the measurement runs out before the planet does, and on the next world, the nearest one to Earth of all of them, it runs out completely. This one is 4 light years away, not 400, not 1800, 4.24, the closest star to our own, the nearest planet outside this solar system, the first place any probe we ever build will be aimed at. And of the 13 worlds in this film, it is the one we can say the least about, not because nobody has looked, because of the angle we happen to be looking from. It is called Proxima Centauri b. It goes round a small red dwarf once every 11 days, at 1/21st of the distance between the Earth and the Sun, and the arithmetic puts it at 218 Kelvin, 55 degrees below freezing. The star is worth a moment, because unlike the planet, it is extremely well measured. Proxima Centauri is a red dwarf of about 1/8 of the Sun's mass and 1/7 of its width, roughly 1.5 times the size of Jupiter. Its surface sits at 2,900 degrees, half the temperature of ours. It is the nearest star to the Sun. It has been watched continuously for over a century, and almost everything about it is known to a precision the planet will never enjoy. That contrast is the shape of this chapter. We know the lamp in detail. We know almost nothing about the thing standing next to it. Now the 2 things this film needs and cannot get. The first is mass. There is a number in the catalogue, 1.055 Earth masses, and next to it, a note that changes what it means. The note says M sin I. Here is what that stands for. This planet was not found by watching it cross its star. It was found by watching the star move. A planet pulls on its star, and the star swings in a small circle, and if part of that swing is toward us and away from us, we can see it in the color of the light, but only the part along our line of sight. If the orbit is tilted relative to us, some of the star's motion is sideways, and sideways motion does not change the color at all. It is invisible to the method, so the measurement does not return the mass. It returns the mass multiplied by the sign of the tilt, and nobody knows the tilt. If we happen to be looking at that orbit edge on, the answer is 1.05 Earth masses, almost exactly our world. If the orbit is tilted 30 degrees, the true mass is 2.11, twice Earth. At 10 degrees, it is 6.08, 6 Earths. Every one of those is consistent with the measurement. The 1.055 is not what Proxima b weighs. It is the least it could possibly weigh. You will read almost everywhere that Proxima b is about the mass of Earth. That sentence takes a flaw and reports it as a fact, and it is the most repeated error about this planet. And there is no clever way around it from here. The tilt is not a number waiting to be measured better. It is information the method physically does not carry. A more sensitive instrument measures the same quantity more precisely. It returns a sharper value of mass times the sine of an angle, and still not the angle. There are ways to break the ambiguity, but they need something else. Catching a transit, or resolving the planet directly, or watching the star's position shift sideways on the sky by an amount far smaller than anything yet achieved for a world this size. None of those has worked here. That is the first problem. The second is worse. There is no radius. Not an uncertain one, not a modeled one. The field is empty, and it will stay empty, because Proxima b does not pass in front of its star from where we are sitting. Transits are how small planets get measured. The planet crosses, the light dips. The depth of the dip gives the width. It is the one clean measurement in this whole business, and it requires the orbit to be lined up with our line of sight closely enough for the planet to cross the disk. Proxima b's is not. From our angle it goes above or below the star every 11 days forever. There is no dip to measure. There never will be from here, so put the two together and look at what this chapter actually has. Gravity is mass divided by radius squared. The mass is a floor with no ceiling. The radius does not exist. There is no arithmetic to do. Not a rough one, not a hedged one, not a model with a warning attached. In the last two chapters, this film could at least sketch the range and show you the ends of it. Here there is nothing to put in either half of the fraction. This is the only world in the film where the question cannot be answered at all. Not answered badly, not answered with a wide error bar. There is no expression to evaluate, because one of its two terms was never obtained and the other has only a lower bound. And now hold that next to the distance, because this is the part worth sitting with. Kepler 452b is 1,799 light-years away, and we have its width to 2 decimal places. Proxima b is 4.24 light-years away, 400 times closer, and we do not have its width at all. Distance was never what stopped us. Geometry was. That planet is not hiding. It is not too faint, or too small, or too far. It orbits the nearest star there is, and it has been studied harder than almost any world in this film. The only thing wrong is the angle. Its orbit does not happen to line up with our eye, and that single accident of perspective removes an entire measurement that a much more distant planet gives up freely. There is no fixing it by trying harder. You would have to move, not metaphorically. To see Proxima b cross its star, you would need to observe from somewhere the geometry lines up, a vantage point displaced far enough from the sun to change the angle, which for a system 4 light-years away means a displacement measured in light-years. The measurement is not hard. It is unavailable from this address. What can be said, honestly, is small and worth saying carefully. It is at least the mass of the Earth, and possibly several times that. It sits at 11 days from a cool red star, which puts it in the zone where water could be liquid if it has an atmosphere, and if that atmosphere has survived, and red dwarfs flare, so the second condition is real. Its calculated temperature is 55 below, which describes an airless rock and tells you nothing about a world with air. And there is a further complication that has nothing to do with the weight. At 1/21st of Earth's distance from the Sun, a planet is almost certainly tidally locked, one face held permanently toward the star, one face in permanent night. That is the expectation for any world this close to a small star, and it was the expectation for the Trappist worlds too. Expectation is not observation. Nobody has seen this planet turn or not turn. Whether you would weigh 60 kilograms there or 200, nobody on Earth can tell you. Stand there then, in the most honest way this film has managed. You do not know what you weigh. You do not know if the ground is rock or ice or ocean. You do not know if there is air. The star overhead is small and red and does not move, and it is the nearest star to home, close enough that our own sun would be visible from that sky as an ordinary bright point, one of the brighter ones, unremarkable among thousands. Voyager 1, at 17 kilometers a second, would need about 75,000 years to get there. 75,000 years to reach the nearest one. Everything else in this film is further. 13 worlds now, and the arithmetic has run out entirely. For 10 of them, this film gave you a number and showed you the arithmetic. For the 11th, a range. For the 12th, a ceiling. For this one, nothing at all, and it is the closest of them by a factor of 400. The weight was never what stopped you. What stops you in the end is the angle you happen to be looking from, and there is exactly one world left where none of that applies. You are standing on the last one. You have been standing on it the entire time. Right now, wherever you are, whatever you are lying on, the final world in this film is the one already holding you up. And here is its number, 1.000 gravities. An 80-kilogram person weighs 80 kilograms. That is not a discovery. It is a definition. Every figure in this film has been expressed in Earth gravities, the Moon at 0.165, Mars at 0.378, LHS 1140b at 1.871. All of those are ratios, and the thing they are ratios to is this. Earth's gravity is one the way the meter is 1 meter long. We built the ruler out of the floor we happen to be standing on. So the interesting number is not 1. The interesting number is 5.514 grams per cubic centimeter. That is Earth's density, and it is the highest of any planet in this solar system. Not Jupiter, which is mostly hydrogen and barely holds together. Not Venus, which is close. This one, there is more iron packed into this ball per liter than into anything else orbiting the Sun. That is what you are standing on. The densest planet in this system, arranged into a well of exactly the depth your body was built at the bottom of. And the density is not decoration. It is why the number is 1. Gravity at a surface depends on how much mass is underneath you and how far you are from the middle of it. The same arithmetic this film has done 14 times. Earth is small compared with the giants, but it is packed hard. Iron in the core, rock above it, very little of the light material that swells the outer planets. A world of this size made of ice would pull far less. A world of this size made of hydrogen would barely pull at all. Consider what that means precisely. Your bones are not generically strong. They are strong to a specification. Bone is living tissue that adds material where it is loaded and removes it where it is not, and the load it has been calibrated against, for every generation that has ever existed, is this exact pull. Take it away for 6 months, and the skeleton starts dismantling itself, because from the bone's point of view the material has become unnecessary. Your blood is under a pressure chosen by this number. Your heart lifts it about 30 centimeters from chest to skull against exactly this force, and the valves in your legs exist because this force is trying to keep it down there. The fluid in your inner ear settles at this rate. That is how you know which way up you are. Every sense of balance you have ever had is a measurement of this one figure, taken continuously, since before you could walk. You do not experience gravity as a force. You experience it as the shape of normal. We know this because we have taken people out of it. Astronauts on long missions lose bone from the load-bearing parts of the skeleton, the hips, the spine, the legs. at a rate measured in percent per month, while the bones of the skull and the arms, which carry very little weight here, barely change. The body is not weakening at random. It is recalculating correctly for the environment it now finds itself in. Their hearts shrink slightly, because a heart that no longer has to push blood uphill needs less muscle. The fluid that normally pools in the legs moves into the chest and the face. The spine lengthens by a few centimeters because the discs between the vertebrae are no longer being compressed. None of that is damage in the ordinary sense. It is a body doing exactly what it should, given a number that has changed, and it runs backwards when they come home. The bone returns, slowly and not always completely. The heart rebuilds. The spine settles back down. For the first days, there is a peculiar heaviness that has nothing to do with tiredness, the sensation of a body being reminded what one gravity actually costs by an environment it had already written off. That is the closest anyone has come to feeling this number as a number rather than as the floor. It requires leaving. Now put the whole film on one line. The Moon, 0.165. Mars, 0.378. Venus, 0.904. Earth, 1. LHS 1140C 1.18. K218b 1.59. LHS 1140b 1.87. Jupiter 2.356. Notice where we are on it. Not at the bottom. Not at the top. Somewhere in the middle, with worlds lighter than this one and worlds heavier, and no particular claim to the center, except that we are the ones doing the measuring. And notice something else, which is the point this film has been walking toward for 14 chapters. On the Moon, the gravity was survivable. What would have killed you was that there is no air. On Venus, the gravity was 9/10 of home, barely a difference. What would have killed you was 93 atmospheres of pressure and 460 degrees. On Titan, you could have flown with cardboard wings. What would have killed you was 179 below. On Jupiter, there was no ground to have gravity on. At TRAPPIST-1, the planet was fine. The star was the problem. On K218b, the arithmetic was clean and there may be no flaw for it to describe. And in the last 3 chapters, the measurement itself gave out a mass with no radius, a ceiling with no floor, an angle we cannot see past. 14 worlds. Not one of them was going to kill you with its weight. The weight was never the thing. It was the air, the pressure, the cold, the star, the missing ground, and finally, the limits of what can be known from here. Gravity was the one thing that was survivable nearly everywhere, the number this film kept computing, and the number that kept not mattering, which leaves the honest question at the end of it. If gravity is survivable almost everywhere, and everything else is not, then what is actually rare is not this number. It is the combination: air at a pressure your lungs can use, a temperature liquid water tolerates, a surface, a star that does not flare, and a pull that your bones happen to have been built against because they were built here. We have not found that combination anywhere else. That is not the same as saying it is not out there. 3 chapters ago, this film could not even establish what a planet 4 light years away weighs. Absence of measurement is not absence of worlds, but it does mean something simpler and harder to argue with. Of the 14 worlds in this film, 13 would kill you. And the 14th is the one you have never had to think about. One last honest number, because this film has tried to be careful with them. Even here, gravity is not exactly 1. It runs from about 9.76 meters per second squared at the equator to 9.83 near the poles. The planet bulges where it spins fastest, and you are further from the center there, 0.7%. You have never noticed it, and you never will, but it is worth saying. At the end of a film that spent 3 chapters admitting what could not be measured, that the one world we can measure completely still does not have a single value. It has an average. We call that average 1, and we build everything else out of it. Voyager 1 at 17 kilometers a second would need no time at all to reach this planet. 14 worlds now. That is all of them, and the film is finished counting. You have weighed 13 kilograms and 188. You have stood on rock that was denser than home and on cloud that may have had no floor underneath it. You have been told 3 times that the answer was not available. And through all of it, you were lying somewhere on the only one that ever worked, at 1.000 gravities, not noticing it at all. That is the last thing worth saying about your body and another world. It is not built for anywhere else. It is built for exactly here, to a tolerance of 0.7%, and it has been quietly holding you against this planet for every second you have been alive.